So I made my stream a slightly worse quality because, it almost feels like every day I have some technical challenges with my PowerPoint doing weird stuff. And a lot of that is the streaming is like CPU intensive. So it just slows everything else down. But the quality, and now it's only 30 frames per second. The resolution's worse. We'll see. Hopefully as time goes on, I will run into less technical problems during the class, because that's been a plague upon me, and I have despised it because it's annoying and it distracts from me actually teaching you all. So, today, again, hopefully we're going to finish 2D kinematics. Last class, I really hammered home, and I'm going to try to keep hammering this X and Y are independent. That is going to be true of like everything, any vector you've ever covered, ever. X and Y are independent. Velocity, X and Y are independent. Acceleration, X and Y are independent. When we get to forces, X and Y will be independent. When you all get to physics 2 and you talk about electric fields, vectors, X and Y independent. So it's a very, very important concept, and it's something we kind of talked about in the first week where I mentioned vectors. We have to break things into components to add vectors, and in 1D kinematics, we have to split into X and Y to solve those problems. I also did a quick mention where I said, if you toss something upwards, any object, the velocity it leaves your hand with is the exact same velocity it returns to your hand with the exception of when you toss it upwards it's positive, on the way back down it's negative. And I said that you could prove this to yourself, but I kind of flumbled around and didn't quite point to the right equations. If you want to prove that to yourself, that tossing something upwards is the exact opposite of something falling back down to the ground, if you want to prove that velocity-wise, this last equation will do it for you. If I have the initial velocity, so you know that the final velocity is going to be 0 at the top. So if I toss something upwards with 10 meters per second, I know the acceleration, and we know this distance is going to be the same. If I toss something up, the distance to the top is the exact same as the distance to the bottom. This is the same value for both. So literally all that's going to change is these are going to flip. And again, you can use this last equation to prove that for yourself. Now, how do you get the plus or minus? This is actually something I want to point out here as well, that Vs squared equals V naught squared. If you were solving, let's just take for example Vf. Say you were solving this problem and you wanted Vf. You will square root the whole other side. Now, something that we can sometimes forget when we square root is that there's a plus or minus in front of that. Something that we can sometimes get caught up on. So say, you square root this and you get, it's gonna come out as a positive. But the reality is, so let's just, make up numbers. Let's say that Vf squared equaled 100. There's two solutions to that. Positive 10 squared is 100, and negative 10 squared is 100. Both are acceptable solutions, so when you square root it, there's actually a plus or minus there, and that's a subtle thing, but it matters, because positive velocity is up, negative velocity is down. And so, for example, if you go ahead and you're like, I want to prove this to myself, that if I toss something upwards, it has the same velocity as tossing it downwards. Let's see, where's that at? Nope, that's somewhere in here. If you want to prove that for yourself, when you end up square rooting it, you'll have to recognize, going down is negative. Okay? So, I just wanted to mention that, and then once you realize that the velocities are the same, you can then use another kinematics equation. So, just wanted to say again, anything I tell you all, you can prove for yourself, as long as you trust the equations. And if you don't trust the equations, then we can kind of talk about that. That's kind of a more conceptual understanding. But if we take the equations as true, most of the things I tell you can be proven by the math as well. So, the maths represent the concepts. Anyway, but we're going to need this idea today. We're going to talk about projectile motion. That's going to be the name of the game today. 2D, so we're going to finish up the problem that I started last time. And then we're basically just get into a whole bunch of things getting launched across some space. Launched through the air. Those are the classic two-dimensional problems. It's going to be a good time. So, last class, let's finish this up. This will kind of be a good recap for us. So, this is the problem we left with, and I kind of got some of it set up, but ran out of time to finish it. So, I said a boat leaves a dock at t equals 0 and heads out into a lake with an acceleration of 2.0 meters per second squared. And it was a little subtle here. I'm going to go ahead and quickly extend this box a bit so it's a little bit more obvious. There was an I hat after that. It kind of got put onto the next line. It may not have been clear, but an acceleration of 2.0 meters per second squared I hat, so that's in the x direction. And a strong wind is pushing the boat, giving it some initial velocity of 2.0 I hat plus 1.0 j hat. And in fact, I'll even clarify, instead of additional, I'm going to put initial, because I think that's better worded. An initial velocity of that. The question asks, what is the velocity of the boat at t equals 10 seconds? What is the position of the boat at t equals... Okay, what is the velocity of the boat at t equals 10 seconds? What is the position of the boat at t equals 10 seconds? And then draw a sketch. So I'm just going to do the velocity and position. I'm not going to do the trajectory because that's going to take more time than it's worth, but the picture's there and I'll let you all look through that. So we wrote down our givens. The acceleration in the x direction is 2 because that's given right here, 2.0 ms squared. We then had the initial velocity in the x direction, that's 2.0 ms. And then we have the initial velocity in the y direction is 1.0 ms. I also noted here that at no point in this problem does it say I'm accelerating in the y direction. So therefore, my acceleration in the y direction is 0. If it does not state there's an acceleration in the y direction and it's not falling through the air, it's not in the air, then we can assume it's 0. And that means that my initial y velocity and my final velocity are going to be the same. If it is not accelerating, it is not speeding up, it is not slowing down, it is not changing direction. Okay? And remember, x and y's are separate here. So just because it's accelerating in the x, that has 0 effect on the velocity in the y. Okay? And then we got our t equals 10 seconds, and yeah, we're going to find the final velocity to begin with. Specifically, the velocity at 10 seconds. Okay. So we are given acceleration. We are given velocity. It's not necessarily explicit here. It does not say where we start. So if it doesn't say where you start, you get to decide. Pro tip, start at 0. Always start at initial. If it does not say otherwise, assume you can set your reference point to be anywhere, but I highly recommend that you set your starting point at 0. That's just probably what you would guess to do, and that's a good intuition to do as well. So that's not maybe written here. Let's go ahead. X naught is 0, Y naught is 0. It is not, this is generally not something that you'll necessarily have to start writing down as time goes on. You'll just get in the habit of it not saying otherwise at 0. But just to be thorough, let's put that there. Okay, so this problem is literally just find final velocity given this information. So, give you all a few seconds. What equation, given initial velocities, given acceleration, given time, given position, what would be an equation that would let us find final velocity? This is the thought process for solving kinematics problems. Write down your givens, write down your missing. What equation will allow me to solve for my missing, given the information I have? There's the big old list of equations. All right. For the grand reveal, it's the first one. The velocity at 10 seconds, so the velocity at some time is given by the initial velocity plus the acceleration at that time. Everything gets vectors. Now, the key here, what makes this different from a 1D kinematics problem, is I need to do that. So my final velocity in the y, using this, will equal my initial velocity in the y, plus my acceleration in the y, plus at. And then I do the same thing. My final velocity in the x equals my initial velocity in the x, plus my acceleration in the x, times time. The key to two-dimensional problems is we love one-dimensional problems so much, we get to do them twice. That's kind of how these things work out. Sometimes you use the same equation, sometimes there'll be different equations. Sometimes you have different information in the x and different information in the y. So you got to pick and choose. All right, so step 4, going to be a very simple calculation. VFY at 10 seconds is going to equal 1.0. That's my initial velocity in the y, plus 0 times 20, and shock and awe, it equals 1. We actually already said this in the beginning, so it's kind of further clarification that, if there's no acceleration. Now, we had to recognize there was no acceleration to make that happen. That was kind of the challenge to this. So that one's real simple. The x1 is also not going to be bad mathematically, fairly good. So 2 plus 2 times 20. So my initial x velocity plus my acceleration in the x times time, and that should come out to 42 meters per second. Okay. Now, we have some options here. I'm not 100% on how I asked for how this one gives the answer. Yeah.
Why is T20?
Oh, thank you. 10. Good catch. Which will change our answer to 22. Thank you. So, I don't know, yeah, please, anytime I do something silly like that, let me know. Now, we can represent this answer in two ways. It says, what is the velocity? So we can do vector notation. So I'm going to go ahead and take all this, shrink it a bit. So one way we could report the solution, and I'll try to be more clear. If this was a test question, I would specifically say, give the answer in vector notation. So that would kind of tell you what I wanted. So the velocity vector would be at time equals 10 seconds, would end up being 1.0 I hat plus 22. Oh, got those backwards. Be careful. Don't mix up your x's and y's. Almost made that mistake. You're so used to x being first and y being second that I took the y again. Those are the kind of mistakes that happen, and you got to be really careful of them. 22 I hat plus 1.0 j hat. Make certain your i's is j's and your y's are j's and your x's are i's. And then it is important, we'll just kind of chuck the units here at the end in parentheses. And there you go, that's our velocity vector. That's one way to represent the velocity. The other way, and probably the more common way, is it would say, what is the magnitude of the velocity and in what direction? What is the magnitude of the velocity and in what direction? To do that, we are going to combine, it's a triangle, y'all. Our final answer here was 22 meters per second this way, and then a little dinky 1 meter per second this way. 22 in the x direction, 1 in the y direction. That gives us our net velocity. If we want to get the magnitude of that, that's traditionally kind of how we may write the magnitude. Not absolute value. I don't want to do absolute value. Do that. So the velocity, if I want the magnitude of it, the total amount, we're going to square that 22 plus 1 squared. There is no way I'm going to do that in my head. Square roots, if you can do them in your head, kudos to you. You're a better woman or man than me. So square root of 22 squared plus 1 squared. And we get an answer that's very close to that 22 because the 1's not doing very much. So that is my net velocity. That tells us how big the velocity is. And then the last step, if I said the magnitude and the direction, we need this angle. We need that little angle there. And that angle is going to be tan inverse. Angle is going to be tan inverse of opposite over adjacent. My opposite is 1. My adjacent is 22. So y over x. Make certain your calculator is in degrees mode. And you'll get 2.6 degrees. Boom. And then we put boxes around our answers because after seeing all of this stuff, it's really hard to keep track of what that, like, okay, great, what's the final answer? So when you all do solve the free response questions on the test, please put boxes around your answers. It makes grading so much easier. It removes ambiguity. So there they are. Fantastic. And we look at this and see if it makes sense. Teaching this class is actually, I told you all it's a 4-step problem-solving process. If I teach this future, I might start calling it a 6-step. First step, draw the picture. Next step, write your givens. After that, what's missing. After that, find the equation. After that, solve. After that, the step that a lot of people forget to do. Does it make sense? Does it actually make sense? Does this answer seem reasonable? We're accelerating 2 meters per second squared every second. So yeah, after 10 seconds, my velocity should have gone up by 20, because every second it's going up by 2. So then that matches up. 22 meters per second for a boat. Again, that's around that 23. It's around 60 miles per hour. It's fairly fast, but there's lots of fast boats. It's not crazy, but it is kind of fast. So this problem probably would have been better if I made the acceleration a little bit less. It's real hard to accelerate that much for that long, I suppose, but it's okay. And then we check our angle and see if that makes sense. And because we drew that picture, we can see, yeah, it should be a small angle. I didn't draw the picture to scale. Would have been very hard to draw it to scale in here because 1 compared to 22, it's kind of small. But again, those are the things you want to get in practice of. Right now, we're just solving problems. When you're in college, the stakes are low. It's your grade, which may seem like a big stake, but no one's going to die if you mess up the math. Later on in life, there's bigger consequences to whatever you may be doing. If you're a civil engineer and your answers don't make sense and you build a building a certain way, people could literally die. Aerospace engineering, people are in planes. They could die. All sorts of more significant consequences. So it's good to check your work, and this is one way to guarantee to have a better chance of avoiding those mistakes. Working together with someone is another way. Doing the math again is another way. There's lots of ways to check your work. All of them should be employed because you will make mistakes. And if no one catches them, there will be consequences. It's just a matter of how big are those consequences. All right. Or you can go into teaching, and the worst case scenario is someone just points out you made a mistake, and there you go. So I've entered a low-risk environment. So there you go. All right, great problem. What is the position? You're just going to use a different equation. I'm not going to go through that one because that's more this. Honestly, okay, great. Pick the final position and plug in the numbers. That's fairly straightforward at this point. You want to find final velocity? Great. Use this one. You want to find final position? We know initial position. We know initial velocity. We know acceleration. We know time. It's just plugging in numbers and solving, and then going through that same process at the end. But if you're stumped on any of this, come by at the end of class, shoot me an email. Any of those things are good. Yeah?
Why does V of t, or you can also say that's final velocity?
Yeah. So that's it. Why? Because you've seen me probably do this interchangeably. We got like VFs, and then we got V of t. So V of t here is the velocity at some time, which is always going to be a later time than when I started. So VF and V of t are basically interchangeable. X of t and XF, interchangeable. So if you wanted to, if it made you, like, this and this are both correct for the equation. Same thing with this one. If I wanted to, I could instead put XF equals X naught plus V naught t plus 1/2 AT squared. Same exact thing. Yep, it's a good question. So it's good to know these are interchangeable. You kind of got to pick one. They both have arguments for why one is better than the other. So they're both good, though. They're both correct. Same thing. All right. Let's get into some projectile motion, y'all. So I'm really tempted to throw my water bottle across the room, but the floor is disgusting, and I want to also drink out of my water bottle. If it was empty, I would do it. But I still want to drink out of it, and I don't trust this floor. So, pretend, I can throw, what can I throw? Piece of paper. All right, I toss a piece of paper across the room. At all times in its flight, what is the acceleration in the y direction? Anything flying through the air that is not powered by a rocket or any engine It is pure, it's just flying through the ice. The only force acting on it is gravity. What is the acceleration in the y direction? We'll go to 50 seconds on, we'll go to a minute. No math required here, y'all. See that you know what you don't situation? In 5, 4, 3, 2, 1. All right. Again, this is a you know it or you don't situation. What makes things fall? Gravity. Negative 9.8. Acceleration is a vector. The negative is going to matter a lot. Fantastic job, everyone. Very, very important that you all remember if something's in the air, no matter where. On the way up, negative 9.8 meters per second squared. At the top, negative 9.8 meters per second squared. On the way down, negative 9.8 meters per second squared. At all points, the acceleration in the y direction. The acceleration in the y direction is negative 9.8 meters per second squared. What about in the x direction? Same problem. I toss it across the room. What is my acceleration in the x direction? Is it 0 ms squared? Is it 9.8 ms squared? Is it negative 9.8 ms squared? Or is it d, not enough information? And I'm specifically saying after it leaves my hand. After it's left my hand and I am no longer touching it. Very important distinction. Same thing, we'll go to a minute. Ooh, good. Yeah, I'm on this. All right, 5, 4, 3, 2, 1. Now, I've mentioned this before, and I maybe should have clarified here. We are assuming no air resistance, and every problem we do here, we are assuming no air resistance because that would be impossible to calculate. So that's just that is an assumption that you basically just, if you see a problem like this, assume no air resistance. You know, ideally that would always be said, but the reality is that's just going to be an assumption for every single problem. In fact, there's only air resistance if I tell you there's air resistance. That's more so. So, to that end, what is the acceleration? Once it leaves my hand, nothing is pushing or pulling it except gravity. Gravity is the only thing pushing or pulling it, and gravity is only down. So in the x direction, x and y are separate. There is no acceleration in the x direction. When something gets tossed through the air, the velocity, the initial velocity in the x direction is the same velocity the entire time. The velocity in the x direction does not change. If it left my hand with an x velocity of 5 meters per second, it's 5 meters per second in the x direction here, 5 meters per second here, 5 meters per second here, 5 meters per second here. The only component of velocity that is changing is the y component. Okay? And this is one that really trips people up. This is a major thing to solving these problems is recognizing the y direction is the only thing whose velocity is changing. The x direction, it is always the same. So if we kind of draw a picture of this, and it doesn't matter where the ball starts. It could start above ground. It could start at ground. It doesn't matter how hard you kick it. It doesn't matter what direction it's going. If I break this vector, and we're going to be doing this today, into its x component, so this is my velocity. If I break it into its y component and its x component, so we'll call these initials. The x component here, it's the same as the other one. Vx, it's the same value here. I don't like to call it Vxf, but Vx, Vx, Vx. At all points, these are all the same. All the same. AX equals 0. Now, if there's air resistance, yes, it will slow it down. But we're not dealing with air resistance in these problems, y'all. And the reality is, even when I toss this ball, the effective air resistance is negligible. It is not that big of a deal. So it may seem like that's a big assumption. For most things, it's not. For most things, if we accounted for air resistance, it really wouldn't affect the answer that much. As weird as that sounds. Most things we throw, we're not really dealing with air resistance much. Now, yes, if you're going really fast, like a plane, and there's a lot of air hitting you, then that matters. If I throw something that's really not aerodynamic, like my backpack, maybe. But most things that are flying through the air are purposely aerodynamic to reduce air resistance to the point that air resistance doesn't really matter much. In aerospace, yeah, y'all got to worry about that stuff eventually. Way later. One step at a time. For now, let's pretend it doesn't exist. Okay. Look at that. All caps, bolded, because it is such an important concept to solving these problems. Gravity is always down. Gravity does not affect anything in the x direction except time. Gravity, and we're going to see, like I got some weird things like gravity affecting time. Because if I throw this thing to the right, the time of flight is purely determined by when it hits the ground. And when does it hit the ground? That's purely dependent upon the y direction. It goes from here to the ground. The time it takes to go from here through the air to the ground, that is the only thing that affects the time. Assuming that the ground is what it hits. Now, there is two different types of problems I'm going to give you all. There's types of problems where it hits the ground first, and there's types of problems where it hits a wall first. The one that's going to depend upon the time, the one that's going to affect the time is, does it hit the ground first? Okay, the y direction, that's what matters. That's the one that's going to determine time. If it hits the wall first, the x is going to be what affects the time. So, we're going to see that when we solve some problems. Really at this point, it's just solving problems. Like, I'll show you all some pictures, but that's really the only way to get better at these projectile motions is seeing a bunch of examples of them. And there's only a few types. Okay, so just this is some trajectory, some nomenclature, nothing really fancy. You probably know what most of these words mean. Trajectory is kind of the path it takes. Time of flight is how much time it's in the air from when it leaves wherever to when it hits whatever. The range is the horizontal displacement, so the range is how far it goes left, right. And the maximum height is how high it goes vertically. Again, these hopefully kind of match what you expect, but it's good to make certain we're knowing exactly what they mean. Yeah.
When you say that it's time in the air, like, do you mean before it hits its first obstacle?
Yes.
Meaning like wall or floor?
Yes. Yeah. So for example, if I throw this piece of paper at the wall, the time of flight's till when it hits the wall. I will never have you calculate it bouncing off the wall and then falling to the floor because that's just a whole mess. So the time of flight there would be till it hits something. An example in your all's problem set is a dartboard. So it throws it, it sticks to the wall, so you don't have to deal with it bouncing off it. So any of those ones where it hits a wall, it'll stick to that wall, so you don't have to worry about afterwards. Otherwise, yeah, time of flight would be when it hits the ground. We do not care what happens after it hits the ground, because that's really complicated. For now, we're just worried about while it's in the air. The second it hits the ground, we're done. To that end, another thing that's kind of important to point out, obviously when something hits the ground, it will eventually stop. We're not, the final velocity, whenever we do a problem like this, and I say, what's the velocity when it hits the ground? I don't want an answer of 0. That's not when I'm asking the velocity when it hits the ground, I'm basically saying like right before it hits the ground. Yes, obviously if something hits the ground, it's going to stop. What I care about is the velocity right before it hits it. That's the interesting part. How fast does it hit the ground at before it comes to a stop? Imagine you getting hit by a football. So let's say that shouldn't have hurt. The football stopped when it hit you. It was only traveling 0 meters per second at the end. No, it hit you moving. That's what we care about. How fast it's moving when it hits you, not after it ended. That's not very interesting. All right. Again, this is just nomenclature. This is not a math problem here. This is just showing you if the thing explodes in the air. I'm not going to give you anything that explodes in the air because that's pretty funky. But this just shows you that the range would be the horizontal here and the height is there. There you go. Okay, again, just showing you what these problems kind of look like. We'll actually solve some of these. This is not what I'm solving. I am just showing you pictures of what projectile motion look like. Okay, so how do you solve these problems? Split everything into x and y, just like we've been doing. Determine what limits the time. I've already mentioned this. Is it the up, down? Is it when it hits the ground? Or does it hit the wall first, if there even is a wall? If it hits the wall first, x limits it. Because when it hits that distance, you know, say there's that wall there, who cares how, when it hits if I throw this thing at the wall is what determined how far I was from the wall. That's what determined when it stopped moving, assuming it's like a dart and stuck to the wall. Whereas if I throw it and it hits the ground, it's when it hits the ground, that's when it determines. So ground is the y, wall is the x. And we're going to see some problems about kind of both examples of those. Whether today or we'll roll into Monday, we'll see. All right, great. See if you are paying attention. A dart is tossed on a dartboard across the room. Which component determines the time? X, Y, or neither? All right, we'll go to 40 seconds for this. Fairly straightforward. Yeah.
Would range be the same as like just x?
Yes. Yeah. Range is the displacement in the x direction. Yep. And then final x minus initial x. All right. And 5, 4, 3, 2, 1. All right. It's the x direction. Hits the wall. Now, let's kind of show in practice what this would mean. This would mean if I threw something, so here's my initial velocity, and you know, there I am in all my personness. If I throw something, here's the wall, how would I find this time? First, I'm going to break this into its components. Because remember, everything has to be done in components. So if I give you a velocity in the beginning, and it's just up at an angle, we need to break that into my x, my initial x, and my initial y. Okay? Great. We do all that. And you know, I would give you this angle. I'd have to give you that angle to do that. So we'd find the x component. So we'd find that, do some trigonometry, we'll get some practice there. It would be the cosine times that, whatever. And then you would just do this. If I knew this distance, let's call this delta x. If the beautiful thing about the x direction in these problems, remember, no acceleration, constant velocity. If something has a constant velocity, we get the simplest equation ever. Delta x equals vxt. Easy way to understand. So this equation kind of comes from the ones I showed you, and we've kind of mentioned it before. Just think of it, if you're traveling 60 miles per hour, that's your velocity. How far do you travel in 3 hours? You just multiply 60 times 30 and you get 180, and that's how far you travel in 3 hours. So if you're traveling at a constant velocity, we get to use this super simple equation. It's wonderful. It's so easy. And so if I wanted this time, boom, just delta x over vx and we're done. And then I could use that time in the y direction to figure out how high it goes and all that. That would be my time of flight. That would be the time between when it leaves my hand to when it hits the wall. Okay? So x direction is actually the nice one. X direction is real because there's no acceleration, so we can just use a super simple equation. All right. A cannon shoots Joe Schmo through the air, after which he lands in a nice comfy net on the ground. Which component determines time? We'll go to 40 seconds as well. All right, in 5, 4, 3, 2, 1. All right, you know, it's not a wall, it's the floor, so it's going to be the y component. So let's go ahead and do the same thing. And you know what? Let's make this kind of the worst case scenario. If the cannon was on the ground, that's a little bit easier, but let's do the worst case scenario. Let's say this thing was up here and at an angle. This cannon could be anywhere. It would be specified in the problem. It would give you the information you need. Gets launched at some velocity, which again has some x component and some y component. And this cannonball is going to go boom, hit the ground. We're trying to find the time it's in the air. This is a critical step to solving these problems, is finding this time. How would you do so? Well, generally we would know this height. We would say this is its initial height here. Well, we know its final height. It's at the ground. And so we'd say, okay, I know my initial y velocity. I found it from a triangle. Great, got that. I know my acceleration in the y direction at all times is negative 9.8 meters per second squared. I know my initial y. I know my final y. So then we say, okay, how do I find time? We go to our equations. Way up here. And we say which equation has time, has initial velocity, has initial position, final position, and acceleration. Spend 10 seconds, see if you can find it. So kind of go one by one. This first one, great, it's got time, so that's good because that's what we're solving for. We know A, we know our initial y velocity, we don't know our final y velocity, so doesn't work. Next one doesn't have time, who cares, can't use that one. Next one, time, oh, it's got final velocity and the y, don't have that, can't use it. Next one, we know our final y position, we know our initial y position, we know our initial y velocity, we know our acceleration. We can find time through the magic of the quadratic formula. Yeah, you all need to know the quadratic formula for this class. It's going to come into play. You will use it in this class and in the future because these equations just pop up at times. Is it a fun equation to use? No, but it is kind of necessary. The alternative is you could actually find the final y velocity using this bottom equation. So you could find the final y velocity by using this bottom one, and then you could plug it into this top one and find the time. That would also work. So you can either use the quadratic formula with one equation, so quadratic formula with this one here, or find VF and plug it in up here and find the time. Whatever sounds better to you, go with that. I probably actually would have chosen the second option because I hate the quadratic formula. There's so many places you can make a mistake, but both work. So pick your poison. If you really like quadratic formula, kudos. Do that. All right. Now, why do we find that time? I keep saying we're going to find the time, we're going to find the time, we're going to find the time. Because that lets you, again, once you have the time, if we have the time, we can easily find that final velocity using this. At the end of the day, we want to know information about this. If we know the time, we can find the final velocity in the y direction. If we know the time, we can figure out how far this thing goes in the x direction. So it lets us discover, remember, at the end of the day, what's the point of doing physics? What's the point of all these equations? It's to be able to predict things. I mean, think of a real world example of this. If you are an artillery officer and you want to hit a target, you better know where it's going to land. And how do you figure out where it's going to land? Physics. Doing the math. The computer nowadays does the math. But without that, what are you going to do? Just keep firing until you hit the thing? That's a terrible decision. One, who knows what you're going to hit before you get the right spot? And, that's an extreme example. But, a more interesting recent example, one of the things they're trying to use with drones is to drop packages off. So one of the things that's cool that they're doing at some place is they're actually delivering blood with these drones. Now these drones don't stop. They just keep going and they drop their package. Well, if they want their package to land somewhere, They need to know the physics to be able to calculate where it's going to end up so it doesn't hit the wrong location. So that's the purpose. This is the purpose of physics. The purpose of figuring all this stuff out is to predict things. The world is logical. The world follows rules. If you know those rules, you can predict what's going to happen in the future given information. And that's very useful because you can't just... There is something to be said about building something to see how it works and then learning stuff from that and then iterating. But if you just start there and you don't do the calculation beforehand, you're going to waste a lot of money. You're going to waste a lot of time. Doing the math beforehand lets you determine, is it even likely that this thing's going to work? That's why you all are learning this. You can't just test forever with infinite resources. So, there's a purpose to this. It's not just for the sake of math. It's to be able to predict things and evaluate, is this going to do what I want it to? If not, revisit your design. Okay, so yeah, I already said that. Vx is constant. It's all, again, just really hammer that in your head real good. And this is a nicer picture than the one I drew. Vx is the same value everywhere, whereas the Vy, if you look at the y component of velocity here it's this, smaller. At the very top, the y velocity is still 0. We learned that before. If you toss something straight up, the y velocity is 0 at the highest point. That's also true when it's flying through the air. At the highest point, the y velocity is still 0, even though it's in 2 dimensions, because everything is separate. Me tossing a ball straight up is the exact same as me tossing a ball to the side, just now it has an x component. Yeah.
That last point, that's kind of like what you were saying about like it's not 0.
Yeah. We want to know right before it hits the ground. We want to know how fast it hits the ground with. Obviously, after it hits the ground, it will stop. But that's not the point. Yeah, the point is to figure out how fast it will hit that thing. Now, in this problem, if you start at here at some height and you end at the same height, the same rules apply. If my y velocity here is 10, my y velocity here is negative 10. The same rules for one dimension apply to 2 dimensions. Now, what's the exception to this? If I launch off of some height that's not 0 and I end up down here. If I launch here and, for example, say the y velocity here is 10, it's going to be faster down here. The y velocity down here is going to be way more than 10. I'm just going to make up a number. You know what? I'm just going to put bigger than 10. I say bigger than 10. I'll put a number there. This is obviously a made-up number. Depends on the problem. It's not double. You know what? Let's make it gross. I really don't want you all to think it's double it. Let's put negative 17.3. Whatever. It's a made-up number. I just want you to see it's still negative, but it's bigger. Now, something interesting. At this exact spot, the y velocity will be negative 10. Because at that spot, it's the same height that it started at. So then it's going to get faster because it's going to fall farther. Yeah.
So say from that second Vy.
Yeah, right here?
Yeah, if that to the third is exactly 1 meter, would that be negative 19.8?
Sorry, if exactly where it was?
Like from the second,
Mhm.
we'll call it all to
Yeah.
the third.
If it was exactly what number?
Would it be negative 19.8 because you're adding the gravity? Or does
Only if it took 1 second to fall that far.
So that's the same, like if it was exactly 1 meter lower.
So 1 meter wouldn't do it. Unfortunately, the math will not be. So that's a great question. If I fall 1 meter, will I increase by gravity, negative 9.8? We can actually just check that out with the math. So xf equals x naught plus v naught t plus 1/2 at squared. Let's just take the simple example. Let's say I drop a ball from 1 meter high. The key here is something will increase by 9.8 if it travels for 1 second. So if dropping something from 1 meter takes 1 second, then yes. But you will actually find, if you do the math here, if I kind of rearrange this, we'll get t equals square root of 2y over a. And if y is 1, it will not turn out to be 1 second. It'll actually turn out to be, let's just calculate that real quick. 2 divided by 9.8, 0.45 seconds. So your velocity, if you drop something from 1 meter, will actually only increase by 0.45 times 9.8. So like 0.46 or something. Yeah. It would be real nice if it worked out that way. But yeah, 1 second of time, my velocity in the y direction will change in the negative direction by 9.8. That exact height that would cause that you can calculate if you so desire. But yeah, that's a great question. Love that. Okay, so let's see if we can start one of these. The good news is I've kind of gotten through the concept. So we are almost caught up from that being a day behind, which is great. So I'm pretty pleased with that. We should be able to get through at least the setup of this. I'll finish these on Monday and we'll kind of get into forces, well, specifically circular motion. So I have an airplane flying, I mentioned that whole dropping blood packet things with drones. They're dropping those to hospitals, by the way, to clarify. You're like, why are people delivering blood? It's, to hospitals. Okay, just to, like, what the heck's going on there? All right, so an airplane flying horizontally. There's my airplane. I guess it's got wings. There they are. With a speed of 500 kilometers per hour. Gross, we're going to have to convert that. At a height of 800 meters. Drops a package. If that parachute fails to open, how far in front of the release point does a crate hit the ground? Again, this is literally what those drones are doing. There's I don't know. You try to look it up so you can find it. But this is literally what the drone does with the thing. It doesn't have a parachute. It just chucks this thing and then it's in a bunch of packaging. And you got enough packaging. They did the same thing to land on Mars at some point. You don't need a parachute if you just put enough of like bubble wrap around something, I suppose. At the end of the day, you just need it to survive. If it survived, you did good. How far, so it's going to drop this crate. The question is, how far is that crate going to land? And we can see here from our picture, that's going to be delta x. So the picture helps us see what our givens are. It helps us see what we're solving for. It helps us visualize the problem and just make certain we're solving what we want to be. So it's flying horizontally with this speed. That means we are so blessed that we do not have to break this into components. So my initial x velocity is 500 kilometers per hour, which would be 500 times 10 to the 3. So I converted kilometers to meters, and now I'm going to divide by the number of seconds in an hour, which is going to be 3,600, 60 times 60. Try this unit conversion out for yourself if you're wondering what the heck I'm doing. Again, I'm kind of blitzing just in these last minutes, but anytime I go quick through this math and you're like, what's going on? That's a great opportunity to kind of think through it, see if you can figure it out. And if you're not certain, shoot me an email. 138.89 ms. We make sure that makes sense. It's a plane. Planes go fast. 500 kilometers per hour. That's fast. So that makes sense. Okay. All right, we have our initial y height is 800 meters. We know our final y height is going to be 0 meters. And as always, we know a in the y direction is negative 9.8 meters per second squared. Okay, and that's all I got so far. Now, remember at any point, okay, we do technically know, we can jot this down, but it's a little superfluous. We know the initial y velocity is 0 because it's all going horizontal. We won't actually end up, maybe we'll use that, we'll see. At any point, if you're solving a problem, you're like, do I have this given? Well, just think through, do you have that? So we're going to see that in a second. I wrote that down. We'll see if we even need it. But when you're writing your givens, if you don't catch everything, just at some point later on, if you feel like there's extra, you can always go back and add. You can always go back and add to that. So we're solving for delta x. And then remember, the x direction is lovely. It's so nice. Because it's a constant velocity. So we can immediately see, to solve this problem, I have the x, yay. I don't have the time. Oh, looks like I'm going to need to find time. And this is where we remind ourselves, when something is in 2 dimensions, when it's a projectile motion problem, you almost always are going to have to find time. Just expect to do that. Just expect that that's going to happen. How do you find time? We say, what's the limiting thing? Is it the x or the y? Am I hitting a wall or am I hitting the floor? I'm hitting the floor. So basically this question is, how long does it take something to fall 800 meters? If I can find how long it takes for something to fall 800 meters, that's how long it's going to be in the air for. Who cares how fast it's going into X? That does not affect the time here. So we'll find the time. Let's see. Yeah, we're at 20. So see if you can figure out how to solve the time. I'll finish this up, but I'm going to go ahead and tell you all it's going to be this. We're going to do this, but great news, y'all. We won't have to do quadratic formula. See for yourself why that's not the case. See if you can solve this one, y'all. It's a great practice. Good luck on the quiz. Work, again, make sure you all know what you're doing. I don't mind if you work together on the quiz. As crazy of an idea it is. I call them quizzes. They're effectively homeworks. I want you to know what you're doing. Whatever it takes to figure out those quiz problems, do it. They're learning opportunities, not necessarily tests. Have a great weekend, y'all.
I hope this